Good afternoon, everyone. I'm very happy to welcome you all to this new academic year 25-26. I wish you a year full of success in every aspect of your life and rich in scientific achievement. It is with great pleasure that I remind you that our Al-Khwarizmi Applied Mathematics webinar has now been running honorably and seriously for 5 years. This success is truly thanks to you, thanks to your continuous presence, your encouragement, and of course, thanks to our speakers who have generously accepted to share their knowledge with us. I sincerely hope that this webinar will continue for many years to come and remain a valuable source of scientific inspiration for all us. Today, we are starting the 6th year of our webinar, and we are honored to welcome our speaker, Dr. Najmuddin Attia. Dr. Attia obtained his master's and postgraduate degree in mathematics at the Faculty of Science of Monastir, then pursued a PhD at Henri Concours and the University of Paris 13, France, under the supervision of Professor Julien Barra. He was appointed as assistant professor at Monastir in 2012 and promoted to associate professor in 2022. The same year, he joined King Faisal University, Saudi Arabia. His research primarily focuses in multifractal analysis of branching random walks on Galton-Watson trees through Hausdorff and Peking measures. He also investigates other fractal measures such as Hewitt-Stromberg and weighted Peking measures, and more recently he has developed an interest in fractal and percolation functions. Today, Dr. Attia will talk to us about relative multifractal analysis of branching random walk on Galton-Watson trees. Thank you very much, dear Najmuddin, for joining us today. And please, you can start.
Okay, thank you, Rafiq. Thank you for all. First, I would like to take this opportunity to thank the organizer to give me this opportunity to present my work. Today, I will compute almost surely and simultaneously the Hausdorff dimension of a set of infinite branches of a boundary of supercritical Galton-Watson tree. This will be in particular for many of you an opportunity to be familiar with Hausdorff dimension and the Galton-Watson tree, I think. So we will start by an introduction to the multifractal analysis of measure. Given a measure mu on a metric space X and fix alpha be a real number and consider the dimension of the measure by this limit. If we consider the set E alpha is the set of X such that the dimension is equal alpha. So the study of this set is central in multifractal analysis. The interest comes from several directions. One, a measure is not always homogeneous, a single scaling exponent. For example, if we take Lebesgue measure, if alpha is equal 1, then E alpha has a full dimension. But if alpha is not equal 1, then this set is empty. So we say that this measure is homogeneous. In general measure,
please,
different part.
Can I ask a question? What do you mean by dimension
yes,
mu?
Of course.
What do you mean by dimension mu
So
of X?
I will explain later because I will work with the Hausdorff dimension, but here the set is empty. That means any dimension is equal 0. Okay. Because if we take Lebesgue measure will be the limit is equal log of R divided by log of R. So is equal always 1. So, but if the set is not empty, so we must study it is empty or not. So, for instance, but in general, if we consider a general measure, different points may have different local scaling exponent. That means for different value of alpha, the set is not empty. So we say that this is a multifractal set. Second, the set of E alpha separate the measure into region where it behaves with a given density exponent. That means we can decompose the support of the measure. This we can understand better the behaviors of the measure mu. Also, in dynamical system, one can consider similar level set when study the set of E alpha describe the point with different long-term behaviors of Birkhoff average. Take an example, the binomial measure. Let us consider the outcomes of the first n coin toss written epsilon1, epsilon2, epsilon n. Each outcome is either 0 or 1, depending on whether the trial is failure or success. Adding them up given Sn, which imply the number of success among the first n trials. The probability of observing this sequence epsilon1, epsilon n is given by MP of this cylinder. So this is called the binomial measure. So you can see in the right how we construct the binomial measure. It's a generalization of the Lebesgue measure. If P is equal half, then we obtain exactly the Lebesgue measure. So it is a generalization of the Lebesgue measure. Now consider the set of E alpha constructed using the binomial measure MP. So the dimension of this measure is the local dimension can be expressed in terms of the digit frequency Sn over n. So study the set of E alpha is turned back to the study of the set of EP. By the law of large number, we have this frequency converge to P. And then the measure MP is carried by the set of EP. So in particular, the set EP is not empty and the set of E alpha is not empty. So for this, we can see that the binomial measure is a multifractal measure. So this is how we study this set in general. Now turn back to our study and consider this family of random walk n, x1, x2, and consider a sequence, a family of IID copy of this family, and let T be the Galton-Watson tree. So what's mean the Galton-Watson tree? In fact, the Galton-Watson tree is an elementary model of the genealogy of a branching population. It describes the evolution of the size of a branching population. Roughly speaking, you can see the graph here, each individual for a given generation gives birth to a random number of children in the next generation. So here in the graph, we have the number of branching is equal to, the number of children is equal to, but in general, Galton-Watson tree, the number of children is a random variable. So here we can see if the expectation of n is bigger than 1. So if each individual gives in mean more than 1 children, then we will say that the tree is supercritical. That means this tree never dies out. We didn't stop. So here we will work in the supercritical case. Also, we will define the boundary of T. The boundary of T, the partial T, is the sequence of infinite word written in the alphabet 1, 2. That means any element of the boundary of T is equal an infinite sequence of 1, 2. For example, 1, 1, 2, 2, 2, 1, and so
on. And sorry, and what do you
Yes.
mean by xi here? For example, x1, what represents x1 and x2?
So here we consider, so in general, we consider this Galton-Watson tree, and in the node, we will put x1, x2, so a random variable, And what ID random variable.
What represents for the parent in the example of Galton-Watson tree? What represents x1, for example?
So it's what is the information. Because if we have the energy of the information, then this information it will be divided randomly into children. So here. So for this, in this kind of model, we assume that with expectation, the expectation of x1 is equal to the sum of expectation of the children. That means we will get the same information.
Okay, so xi equals to xi1 plus xi2 in this example for all I.
Here we consider in our model, in application we usually take this in the physics, but in our model we consider IID because just in the application it's just a normalization.
Okay.
But we suppose that all the random variable are independent.
Okay.
So now if we consider a point T here in the boundary of the tree, so T is a sequence of 1, 2, 1, 1, 2. So we can associate a sequence of random variable here. For example, here we can associate in our tree x1, x1, 2, and so on. So according to the point T. So using we can associate the branching random walk denoted by as n of x. So the boundary of T here is a compact metric space endowed with this distance standard metric dy. So using the law of large number, assuming that the expectation is finite, then now we have as n of x divided by n converge almost surely to the expectation of x. Almost surely. So the question here, can we see some branches or some T where the law of large number doesn't hold? That means as n of x over n converge where another value different from expectation. So this is the question. For this, we will consider the set of E alpha is the set of T, the number of branches, such that as n of x over n converge to alpha. Of course, if we use the standard metric, if alpha is equal to the expectation, this set is full dimension, otherwise the set is empty. But this set is not empty in reality, and we will study the size of this set. So how we will study, we will describe geometrically throughout their Hausdorff and sometimes backing dimension, and we will say that the multifractal formalism holds at a point alpha if this set is not empty and the dimension, the Hausdorff dimension here, is equal to the Legend transform of some function P. This function P usually denoted or called as the pressure. And the Legend transform is defined by this expression, the infimum over Q, P of Q minus Q alpha. So this is our, and the function P is, here we have the definition of the function P. And since we work with the random variable, we will take y tilde P is exactly the same function, but we add this expectation. We will use it in the proof. So our aim is to study this set. So for this, I want to mention that there is two sets in our work. There is the set of I, is the set of alpha such that our set is not empty. And there is the set of G. The set of G is the set of Q. Here we have the relation between I and G. The interior of the set E is equal to the derivative of the gradient at G. That means if we fix Q, if you fix alpha in the interior of I, one can find Q such that alpha is equal to the derivative at P at one point Q. So we have I is the set of alpha and G is the set of Q. So what is we'll know before, to study this kind of set, fix alpha in our set E, I, and alpha surely it is written as the gradient of P at some point Q. We take this Q and we construct the Mandelbrot measure mu Q. And we compute the dimension of the measure. And an application, a direct application of the mass distribution principle gives that the dimension, the Hausdorff dimension of E alpha is bigger than the dimension of the Mandelbrot measure. And since the upper bound is always simple, so we get the desired result. So what's well known before? So expected result. Here we want to prove the result uniformly. That means we will prove almost surely for all alpha we have this result. So there is a difference here. We fix alpha and we prove the result almost surely. That means for x for fixed alpha we have a set with probability 1. But here we have a set with probability 1 which gives the result for all alpha uniformly. So this is what we want to prove, uniform result. And as a consequence, we will get a result related to the large deviation principle, but uniformly. So what is the problem if we work in the boundary of I? So if alpha is in the boundary of I, so there is two cases. Because if alpha is the anterior, then alpha is equal the derivative of some point Q. But if alpha is in the boundary, so there is two cases. The first case, we have also alpha is equal the derivative of at some point Q. But we have the Legend transform is equal 0. And the Legend transform, this is the dimension of the measure. Then this measure is, the dimension of the measure is equal 0. And we cannot use this measure. The second case, alpha is not the derivative at some point, but alpha is equal the limit of some sequence Qn. So in this case, there is not Mandelbrot measure to construct. So you can see there is a problem when study the boundary of I, and this is not will before. So there is some work who study for fixed alpha in the first case or in the second case. But our goal here, or our aim, is to give uniform result for all alpha in the anterior and in the boundary of I without restriction. So uniform result would work for any alpha. And this is what we want to prove. Here, just a remark. Here, we don't take the set E alpha, but we can give the result in general form when K is a compact subset of RD. So if we take K is equal alpha, so we obtain the set E alpha constructed before. So this is what we want to prove. Now we move to how our approach for multifractal analysis in the anterior of I. So our aim is to prove the Hausdorff dimension. So first we will define the Hausdorff measure and dimension. So to measure a size of a fractal set, we cover it with small intervals. We cover with small interval, this one, IG, of length less than delta. Instead of counting interval, we weight them with a power alpha of their length. As delta tends or goes to 0, this process defines the Hausdorff measure at dimension alpha. So for fixed alpha, we construct a Hausdorff measure. So as we change alpha, the Hausdorff measure jumps from infinity to 0 at a critical value called the Hausdorff dimension of the set E. It captures the effective size of fractals larger than a line but smaller but a plane. So in this case, we can construct a set where with the Hausdorff dimension is equal half or 2/3, for example. So we can see that the definition of Hausdorff measure and dimension seems to be not difficult, but also seems to be very difficult to apply it and compute the exact measure of a specific set. But here we have a strong result, which we call it the mass distribution principle, which give the upper bound for any set. So what is this theorem? So assume that there exists an auxiliary measure nu, such that nu is carried by the set E alpha. So first conclusion, our set is not empty, since we construct an auxiliary measure. And assume that the dimension of the measure is bigger than gamma. So we have the strong result, the Hausdorff dimension of our set is bigger than gamma. Since we want to prove that the dimension is bigger than the Legend transform, that means our aim is to construct an auxiliary measure carried by the set E alpha, and the dimension is bigger than the Legend transform. The upper bound, that means dimension of less than gamma, it's always simple. We will not focus here. Always we will focus in the lower bound, bigger than. So our auxiliary measure is in fact the Mandelbrot measure. So always we will construct a Mandelbrot measure to be an auxiliary measure of our work. So for this, we will construct an auxiliary, the Mandelbrot measure in general situation. So first, the Mandelbrot measure is a random measure constructed on the tree. The measure is defined by multiplying. So we consider a tree, and here we have on the node, we have our random variable, IID. So our measure is defined by multiplying weight along each branch of the tree. For each level of the tree, we sum the contribution from all branches to get yn, this sequence yn, which converges to a positive limit y. We can also define the measure rooted at any node given the local version y over u. This one. Finally, the Mandelbrot measure mu assigned a mass to each cylinder proportionally to these product and limits. So this is how we construct on the tree the Mandelbrot measure. So we do the product of all this white. And in fact, this is a generalization of the construction of a Lebesgue measure. So this is, we recall, this is our function P, which will give the result. So as mentioned before, the upper bound is always simple and is based on simple covering or standard covering. So we will not focus here. So what is the idea to prove the lower bound? So we will construct, to get the lower bound for Hausdorff dimension, we construct a family of Mandelbrot measure indexed by Q, mu Q. This is the Mandelbrot measure. These measures are associated with a sequence of weighted vector along the branches of the tree. The weight encode the exponential of a linear from minus a pressure form, minus this function P. So given this weight, now it is simple to construct the Mandelbrot measure. Just we construct our tree and we put on the node the random variable W1 and so on, and we construct as usual the Mandelbrot measure. So here we have Yn is this martingale Yn, and we have the construction of our Mandelbrot measure mu Q. Okay, so here to prove the convergence of Yn in L1 norm, usually we control the series of Yn minus 1. This sequence converge, but here you can see that always we get this approximation phi of PQ, and if we prove that phi of PQ is less than 1, then this is a geometric series and we have the convergence. But in our case, we need a uniform convergence. We need a uniform result. So we need a uniform construction of the Mandelbrot measure mu Q, and we need a uniform convergence of this sequence Yn. So for this, we want to control this one, the series of the supremum on Q of this one. So our aim is to control this series. So here the method relies on an idea of by Begins extended the martingale to complex parameters and using Cauchy's formula. This gives uniform control on the convergence for all parameters in a neighborhood. So our work is based on this idea to control the series and using the Cauchy formula to do this. And then if we already constructed the uniform Mandelbrot measure, now we will check the condition on the mass distribution principle. For this, we prove that in the first proposition that almost surely for all Q, the average of X along a path converges to the gradient of the pressure function. What means this? That means the measure mu Q is carried by the set of E alpha. Next, in the second proposition, we prove that the local dimension of the Mandelbrot measure along typical path equal to the legend transform pressure. That means here the dimension is give the exact value. So a direct application of the mass distribution principle give our result. So an idea to prove the proposition 1 So we consider the sequence Ln, the sequence of generating function Ln for the measure and show that they converge to a limit LQ. This show that the sequence of measures satisfy a large, this sequence muqn, satisfy a large deviation principle. And from this, we deduce or we conclude that almost surely, almost everywhere, almost every path under the measure muq has its empirical average conversion to the expected gradient. In fact, this result is a direct consequence of the large deviation principle. If the sequence satisfy large deviation principle, then we can take this value because this value give 0 for the rate function in the theory of large deviation principle. So this is a direct consequence for the large deviation principle. Now we move to the multifractal analysis in the whole set I, not only in the anterior, because in the anterior, alpha is equal to the derivative of some point q. Now this is not the case. So in this case, we consider rho, we consider here rho is a sequence qk, and we defined a inhomogeneous Mandelbrot measure mirror. So that means here we will not construct homogeneous Mandelbrot measure, non-homogeneous Mandelbrot measure. That means fix rho is equal q1, q2, and so on. In the first generation, we will use the same white as before, but here we use the point q1. Next, we use the point q2, and so on. So this is not homogeneous Mandelbrot measure. So here we can see the figure here. So what here we have of course we will use the mass distribution principle. That means we have a proposition 1 and proposition 2. In the left we have when alpha is equal is in the anterior of I. In the right we have in our case when we use a sequence qk. So we can see the difference, but it's almost the same. Here we have Sn of x over n converge to alpha, but here since there is alpha is not the derivative of q, so it changes slightly, but almost the same. So from this comparison, we need only to prove that alpha is the limit of the gradient and the Legend transform is equal to this limit. So we want to check that there exists a sequence satisfy this condition. So here we recall the set I and the set G. So here we have I is the adherence of the gradient of P at some point Q. That means for any alpha, we can find a sequence which converge to alpha. And this sequence is the gradient of P at some point QK. The upper bound is always simple from the definition, but we will focus on the lower bound of our study. So, of course, we will construct the Mandelbrot measure, inhomogeneous Mandelbrot measure using the sequence mu-rho. And here we can see that if we use the same estimation as before, since we have qk and not fixed q, we will to estimations of the martingale yn, we need to control this series. But phi of pn qk is less than 1, but it's converged to 1. It's converged to 1. So we need to control this sequence qk so that we guarantee the convergence of this series. And this, the idea is to choose the sequence ng so that we guarantee this convergence. For this, we take q1, n1 time, so that then in the next generation, we take q2, n2 time, and so on. So here, the idea is to guarantee the convergence of this sequence. So this is so here we take how to construct the sequence. We take a subset DG, and we choose our sequence QK in these subsets. And also for any beta between 0 and 1, we take the random variable W beta is equal 1 over beta or 0. And this will be used to estimate the Mandelbrot measure from below. That means the dimension is bigger than something. Always here, if, after construction of the Mandelbrot measure, we will prove the proposition 1 to say that this Mandelbrot measure is carried by our set E alpha, and then compute the Hausdorff dimension of the Mandelbrot measure is equal bigger than 0 in this case. So as before, so the only difference here, we construct an inhomogeneous Mandelbrot measure. So an idea to prove the dimension, here we extend the idea of Cahans to our uncountably family of inhomogeneous Mandelbrot measure. For this, we consider the sequence yn is equal to the integral of this white q, and use the integration with respect to the Mandelbrot measure 0. So Cahans introduced this technique, and he studied the convergence of the martingale yn, the sequence yn. If yn doesn't converge to 0, and then we can estimate the dimension of the measure mu. So we use this in our uniform case. So we extend this method in our uniform case, and we get the desired result. So now we finish this part, and we give a general result how to estimate the Hausdorff dimension of the measure E alpha uniformly, simultaneously, and for any alpha in the anterior or in the boundary of our domain. So now if we consider, since for H alpha, because if we consider the anterior of the set I, fix alpha, we can find the Q, and we construct the Mandelbrot measure mu Q. Now, for any alpha, we can construct so many sequence, so many Mandelbrot measure, not only one Mandelbrot measure. So consider the set E alpha and the set E beta for alpha different of beta. So for the set alpha, there exists Mandelbrot measure mu, and for the set E beta, there exists another Mandelbrot measure. So surely, since E beta is different from E alpha, these two measures are singular. Now consider the second case. If we take the same set E alpha, so maybe we can find two different measures which carried by this set E alpha. So it is natural to ask if the two measures are singular. But if we assume that the dimension of mu rho is different from the dimension of mu rho prime, then this measure also are singular. But now, if we consider the same alpha, the same set E alpha, and we can find two or more different measures such that all this measure carried by the set E alpha with the same dimension, so it is natural to ask if it is singular or not. So in fact, if this sequence QK with probability 1, we have QG different from the QG prime for infinitely many G, then the measure mu rho and mu rho prime are mutually singular. So here we understand more these measures are singular or not. This result has a very important application, because if the set of E alpha, assume that the dimension of E alpha is equal 1, so surely the set of E alpha is not empty. But if the dimension of E alpha is equal 0, so we prove in the first part, since we construct the Mandelbrot measure carried by the set of E alpha, so we prove that it is not empty, even the dimension is equal 0. Now, in this second part, we prove that it is not countable. It is uncountable, because E alpha carries uncountably many mutually singular inhomogeneous Mandelbrot measure with the same Hausdorff dimension. So the set is not empty, and it is uncountable. So this is the application of our second part. Now we move to some extension of this result. So the first extension concerning the random metric. So we consider the same notation and we take phi to be a random metric in our Galton-Watson tree. So what is the idea? So since we have a random number of children, so it is natural, it is really natural to construct a random metric or in our Galton-Watson tree. And our result, of course, we will obtain the same result exactly, but our space, the boundary of tree, is endowed with the random metric. So usually, if we study the multifractal analysis, we need to construct set using this form. That means Sn of x over the variable given the random, given the metric. Okay, because here you can see that in the first part, we use Sn of x over n because the metric is exponential minus n. So always we need to, in the denominator, we write the metric. Now, if we want to study, it is natural to write this form as n of x divided by the metric. But in our case, we have as n of x over n. So we need to do some transformation. So as n of x over n, so we do this transformation and we take a condition so that as n of phi is comparable with n. So that if the limit is equal 0, one can remove, one can substitute n by Sn of phi. So this is the idea. But here, the main remark here, so alpha is a parameters, and in fact, we study the level set related to 0. Before, we studied the level set related to alpha. Here, alpha is a parameters and the level set is related to 0. For this, in our theorem, we can see that the dimension is given by the Legendre transform of the level set 0 and x alpha. So this is only the remark. But the proof almost the same. Just we check how to construct the sequence rho and how to construct the sequence ng. Also, we can study the speed of convergence. We can study the speed of convergence. So consider the set E alpha S when S is a sequence and Sn of x minus n alpha is equivalent to Sn. Of course, if Sn is less than n, then of course E alpha S is included in E alpha. So the question, can we find a good condition on the sequence S so that we have this set has a full Hausdorff dimension. That means the dimension of E alpha is equal to the dimension of E alpha S. So our hypothesis here in this context is the following. And so here, and we obtain under this condition the exact result. And the main remark here is how to construct, how to prove this result. Also, we construct the Mandelbrot measure. And here, of course, the Mandelbrot measure will be depending on the sequence S, depending on the sequence S. So, so this is how to prove this result. So the same idea as before. And we prove we use the Mascot distribution principle. So the same idea. So here, if you can see that our sequence Sn is depend of gamma. So from the beginning, we take S is Sn of gamma. Usually one can ask why there is gamma, why this is any sequence Sn. So here I want to write gamma because this comes from the work of Kahan and Fan. The work of Kahan and Fan. So here he proved for a fixed alpha, Kahan using this condition for a fixed alpha to prove this result. So here you can see that Sn is less than n and square root, you can see the condition used by Kahan. So the standard sequence is n power gamma, where gamma is belongs to 1 over 2 and 1. So this is why it is natural to consider this sequence depends on gamma. Even we can write any sequence as. So if we assume now our sequence depends on gamma and we give uniform result. So here our result here is dependent only for fixed gamma. So it is natural to give a uniform result on gamma also. And this is what we change if we do a uniform result on gamma. So we change the hypothesis. So if we summarize this part, so Kahan prove for fixed alpha, and I generalize it for uniform result, and we modify the condition. So thank you for your attention.
Thank you for you, Dr. Attia, for this nice talk. Now, if there are some questions, are there some questions? In the slide 26,
26.
please, yes. 26. 26.
This one, 20.
Okay.
Okay.
Why NQ is a martingale? It is difficult to prove that it is a martingale, or it
No, no,
is.
no, 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 no. This is not. This is a martingale. It's very simple result.
Okay.
It is a
Okay.
martingale, positive martingale, which converge directly to y. There is no
Okay.
proof.
Okay. So,
But in our study, we need the uniform convergence.
so since you have a martingale, I think that we have a lot of results to for the martingale to prove the convergence. Not almost
So,
surely convergence, but other convergence, convergence in L1 and in
yes,
distribution.
yes, but
Yes.
mhm. But in our study, we need the almost surely convergence because we need to construct using this limit. Because we need this limit yq. We need that this limit is not zero almost surely to construct the Mandelbrot measure because we need the Mandelbrot measure, this one.
Okay, so you have to prove that yq is not zero.
Yes, this is what we want, almost surely. There is a set with probability one when
But
we can construct our measure.
but you can use the convergence in L1 since UNQ is a positive martingale. So if it converges in L1, then the mean of YQ is equal to the mean of
Yes,
Y1.
but in
And
the proof we prove in L1 convergence. In the proof we use in L1 convergence.
okay, to prove L1 convergence, it's easy to prove that the mean of Y1 n equals 1 is not equal to 0. It's a physics because
Mhm,
the sequence of means is a constant for the martingale.
mhm.
So the mean of YQ is exactly equals to the mean of Y1.
Yes,
Then it's easy to take n equals 1 and to prove that the mean of Y1 it is not equal 0.
yes.
See, okay, okay.
This is in the simple case. Yes, you are right. But this is our motivation. Since for a fixed alpha, we have a probability space, that means a set with a probability one, that all this is true. But our result is to prove the uniform result. That means find a set with probability one. And in this case, we cannot directly prove that the expectation is equal one of y. For fixed, yes. I fix alpha. I fix alpha. That means I fix q.
Okay,
This is
no,
converge in L1, converge almost surely, and the expectation is equal one. Yes, I agree.
but
But if we
no,
but if
okay,
we change alpha, we change q, we get another set with probability one, such
okay,
that converges the expectation is equal one. So since we have uncountably many q, uncountably, so we cannot. It's not easy to see this. So we need to construct uniform q yn.
uniformly in Q, you mean?
In q.
Okay, okay, okay. Are there other questions, please?
Can I ask questions?
Yes, please, Dr. Dua.
Okay, yeah, thank you so much. Unfortunately, I didn't attend from the beginning, but I have one small question. Is W is related to Wiener process or something, or no? It's something totally different.
Boundary process.
Wiener process.
Say Wiener process, right?
W.
Or no? Yeah, which is,
No.
you write it here in that slide. It's summation product WQU conditional K. So I'm asking, is this W related somehow to Wiener process or not?
No, no. Here in this slide, in this slide, W.
Yes.
Are you hearing
No,
me?
no, no, it's not related. It's just a white of random variable.
Other question, Dr. Dua?
Did you say yes or no? I didn't hear.
I cannot see the relation with this process, with this.
There is no process. There is no connection between them.
Yes, yes, I don't see
Okay.
the relation.
Okay.
Other questions, please? Thank you, Dr. Dua, for your question. Other questions, please? Okay, thank you for the presentation. No questions. Okay, if not, we have to thank again Dr. Attia for his talk.
Thank you for
And,
your.
and for information, our next talk will be after 3 weeks. Thank you. Thank you, Dr. Attia.
Okay, thank you for all.
Thank
Thank
you
you
so
for all.
much.